morning everyone. So in the last class we have exactly seen like what is extendable hashing. So it is one of the hashing technique. The dynamic hashing technique is nothing but your extendable hashing, correct? So now why we need to go for your dynamic hashing technique is suppose say in the real-time scenario the size of the file may grow or the size of the file can get shrink, correct? When you delete the records, size of the file can reduce. So yeah, basically file can grow or shrink based upon the addition of the records or deletion of the records, correct? So now in order to manage with this particular dynamic nature of your file, one of the important dynamic hashing technique is nothing but a extendable hashing. So we have seen in the last class what exactly an extendable hashing is. Basically it contains two things. Just I'm briefing it out so that it will be easy for us to understand the example. So which are the two components? One is nothing but your buckets. So as I told you that buckets are nothing but the pages which you're going to write to the hard disk or read the data from your hard disk. So pages are nothing but I can tell that they are nothing but called as a buckets or the blocks. Okay, buckets, blocks, pages, all those particular stuff. So as we know that each and every bucket has a unique address on your hard disk, which is nothing but called as a physical address. And the number of records that are stored inside each bucket or each block is nothing but called as your blocking factor. And second component, what we are going to come across in your extendable hashing is nothing but your directory. So directory holds two information, or it basically has two parts. So what are the two parts? Basically it has a binary code which is a result of your hashing function. After you apply a hashing function for a particular given key, okay, so you get an address. So basically that address in the form of a binary value to be stored in our directory. And in addition to that, your directory also contains a pointer which will be pointing to the buckets where exactly you'll be storing your records. Okay. So now our two directories entries may point to the same record. So we'll see like in what scenario there may be a situation like two directory entries may point to the same record with an example. So use of directory of pointers to the buckets, that's what I told you. So when you want to insert the records into the bucket, there may be a situation like the bucket size may be full. Number of buckets, number of records inside the bucket may be full. So when the size of the bucket is full, definitely suppose if you want to insert another record, if another record also points to the same address, then definitely you cannot insert that new record into the existing bucket. So what should you do in that scenario? So basically you need to split the bucket. And in sometimes what happens whenever you try to insert, whenever more number of key values are hashing to the same address and you go on splitting the buckets when the bucket is full. So how long you go on splitting the bucket is, okay, so we have something called as a local and global depth. So when the local depth is equal to global depth, till then you can go on basically splitting your bucket. When the global depth and local depth become same, then basically we need to double the size of the directory. So this thing also will be seen with the help of example. So usually why we are moving to this particular directory concept is the size of the directory usually will be very much less compared to the size of the file. So that's the reason whenever you are performing the various file operations, so it will be expensively cheap with respect to the directory. And since we are dealing with one page at a time, splitting, whenever you want to split a particular given bucket into two buckets, the splitting becomes easier because the data entries will be available in the same page. So that is another advantage why we have to move to this extendable hashing. So in this extendable hashing, we'll not find the overflow pages. Like how we had overflow pages in the form of a linked list in case of a static hashing. In case of your dynamic hashing, basically we don't have a concept of the overflow pages. We'll be basically not having. So why is that no overflow pages in case of your extendable hashing is? Because it all depends upon how we are going to adjust with our hash function. That's the reason there is no concept of overflow pages in case of our extendable hashing. So I told you that there are two components involved. See, this is nothing but a directory. This is nothing but a directory. These are nothing but a bucket. See, bucket. I have four buckets, A, B, C, D. So I told you that extendable hashing has two components. One is nothing but a directory. Okay, another one is a buckets. Okay, so now inside this particular buckets, you have the records. Why I have shown as 4 star, 12 star, 32 star, 16 star is basically this bucket stores the actual records. So here I showed only the key values. So the entire records, 4 records, each bucket has a capacity to store 4 records. Now I told you that your directory has 2 parts. See, this is nothing but a binary address what your directory has, and second part of your directory is nothing but a pointer pointing to the appropriate buckets. Correct? So directory will be having 2 parts. One is nothing but a binary code, and second one is the pointers pointing to the appropriate buckets. Okay, so now each bucket, here we have 2 things. One is called as a local and global depth. Okay, global depth will be applicable for the directory and local depth will be applicable for each bucket. So now with a couple of examples in the next slide, we try to understand how does the global and local depth changes. How do you insert a record into a particular bucket? How do you decide that which record should go into which particular bucket, or which record should make use of a particular address in a directory? So that we'll see with a couple of examples. So now here in this particular examples, we have taken, I told you that capacity of each bucket, what we have assumed is 4. So basically the blocking factor is 4. So already we have discussed concept of the blocking factor in the previous classes itself, right? So now we'll move with an example. See, this is again an example, basically what I've taken. So here let us try to understand what exactly a local depth. So local depth, basically this is nothing but a local depth. Usually local depth will be associated with the buckets. Now what is this? So local depth determines how many bits that are required in order to tell that a particular entry belongs to which bucket. See, there are, say, for example, in this example, I have 4 buckets. Suppose, say, I have a particular entry, say 21 is a entry I want to identify, or I want to determine 21 is present, 21 belongs to which bucket I want to identify. So now, how many bits of that particular key value 21 you're going to use in order to determine so which bucket that 21 should go to. So the number of bits that you're going to use to determine which bucket, an entry belongs to which bucket is nothing but called as a local depth. Coming to the second one is nothing but your global depth. So usually the global depth will be associated with the directory. Now what exactly is your global depth? Global depth is nothing but how many bits the number of bits you're going to use in order to identify which bucket an entry belongs to. You need to identify the bucket address, okay, in which your entry belongs to. To identify the bucket in which an entry belongs to identify that how many bits you're going to use. So those number of bits are nothing but called as a global depth of a directory. So max number of bits needed to tell which bucket an entry belongs to. Okay, so this is how basically we define. We'll see with an examples how do we come across these values, local and global depth. Now these are some of the assumptions what we are supposed to consider before we move on to the actual example. Okay, so to find the bucket for suppose say you want to insert a new record. Okay, so what you will be doing, you will take the key value of that particular record. So after taking the key value, that key value of the record should be given as an input to whom? Hashing function, correct? So now in this scenario, we are considering the simple hashing function as h of r. Whatever the key value of that record, you're going to give key value of that record as an input to the hashing function. To the hashing function, we are going to get some address, binary address. So in that binary address, we are going to take the last 2 bits. By taking the last 2 bits of your binary generated address, we have constructed this particular example. Okay. For simplicity, we take height, as I told you that our main intention is not to concentrate on developing an efficient hashing algorithm. Instead, we are trying to understand how our extendable hashing works. That's the reason here we have considered h of r as a simple hashing function, and the output what it gives is nothing but the same value in terms of binary. Okay, for example, h of 5 is equal to 5. Suppose 5 is the key value of the record. So h of 5 results mean the same, that is 5. So that value I'm going to represent in case of binary, that is 101. So now I need to, since I need to take the last 2 bits of the binary value, last 2 bits means 0, 1 I should take. 0, 1 means, so you go to the directory, see where is that 0, 1 address. Yes, 0, 1 address means this is the entry, your directory, you are supposed to move to the directory, 0, 1 entry, and your pointer is pointing and it will take you to the appropriate bucket where that file should get inserted. So you go to that bucket and insert file. Okay, so this is the basic assumptions what we are going to make, and these are the different terminologies what we will be using in the further examples. Okay, as I told you that, suppose say you are trying to insert some values into the entry into bucket A or bucket B. So if you try to insert, no, already the size of the bucket is full. If the size of the bucket is full and the additional record what you want to insert is also producing the same addresses as bucket A and B, then you need to split the buckets. Okay, so that we'll see how to split the bucket, how to do the insertion, all this particular operation in the next slide. Okay, now let me consider one thing. You need to make an assumption here. Suppose if I have only one bucket, then no need of any address, because one bucket, no need of address, no confusion. I can only one bucket I have, it's very clear cut. I can refer to that single bucket. Now suppose say if I have 2 buckets. So if I have 2 buckets, then how do I differentiate one bucket from the other bucket using the binary addressing? So in order to differentiate 2 buckets, I may use one binary digit. Yes, that is 0 to identify one bucket, and one digit 1 is being used to identify the other bucket. So one digit binary address I need, right? So only one digit of binary I have used, one bit of binary I have used in order to identify 2 buckets. Correct. Similarly, if I have, say, for example, 4 buckets, how many bits of addresses are required? Basically, 2 bits of addresses. That is 2 power of 2 becomes what? 4. So on like that. So now here I'm not starting with a 1 bucket. I'm starting with minimum 2 buckets. So how many bits of addressing is required? 1 bit of addressing is required. 0 is used to indicate the first one, and 1 is used to indicate the rest. So basically, I can address 2 buckets using 1 bit. I can address 2 buckets. Correct? So now your global depth is 1, global depth is 1, means how many bits of address I am using here? Only 1 bit of address I am using. So local depth and global depth are said to be 1. Okay, how did we get it here? Say for example, now I want to insert 4. So for example, in this case 4, if I want to insert, we know that I'm going to give 4 as an input to a hashing function. So it generates binary value 100. I need to go for the last digit. So go to 0th entry in your directory. So it is pointing to this. I have inserted 4 here. Correct? So these are nothing but a directory. These are nothing but your buckets, or basically called as a data pages. Now we'll see with the next another successive. We'll start inserting the next successive 3 elements. Okay. See, this is the structure already. We have 4 already we have inserted, and local depth is 1, and this is 1. Now I'm supposed to insert, these are the values I'm supposed to insert 12. For example, 12 means I need to give 12 as an input to hashing function. So it generates me 12. So what's the binary value of that? 1100. So how many bits I need to take here? Because in my extendable hashing, whatever I have in my extendable hashing, basically what do you have here? Okay, so how many bits I need to take from the last? Only 1 bit, because only 1 bit of address I'm using in order to address the directory or the buckets. Only 1 bit. So I need to take the last 1 bit. Okay, 0 means I need to go to the 0th entry in the bucket. So it makes me to point to bucket T. Means to tell that the 12, the record whose key value is 12 should be inserted into the bucket T. Correct? So now see here, 12 goes into the bucket A. Similarly, I have another one, say 32. 32 should be given to a hashing function 32. This is a binary value. Again, in this particular example, how many digits of binary digits I'm using to represent the addressing? Only 1 bit. So I'm taking only the last 1 bit. So it is telling that 32 also should go here. So 32 has gone into the appropriate bucket. So next, let me take 16. 16 also, this is the binary value for 16. So again, it has gone to bucket A itself. Correct? Hope so they are clear. It's clear for all of you. Now let me consider h of 1. So h of 1 binary value if I represent, I need to extract only the one last digit from the binary value, it is 1. So now it has gone here. It has gone to the bucket B, correct? See, what 1, where is the pointer pointing to 1? Okay. Similarly, what we'll be doing is, we'll try to insert few more elements. See, this is the status of the previous example. Now I want to insert, for example, say 5, 21, 30. So 5 I'm going to give as an input to hashing algorithm. This is a binary value. Only one digit I'm going to extract, last one digit. So I'll go here. So it points me to bucket B. I'm going to insert 5 here. Similarly with 21, similarly with 13. So that's what 21 and 31. 13 has moved to the bucket D. Correct. So now till here there was no confusion. Okay, everything was fine. So since there was a space in the buckets A and B, we have inserted. Now let me consider the next scenario. Let me continue the same example. Suppose this was the scenario what we had in the previous slide. Now suppose say I want to insert 10. See, observe carefully. This is very, very important. I want to insert 10 now. So again, 10 will be given as an input to the hashing function. So again, it is simple. Since it's a simple hashing function, 10. What's a binary representation of 10? 1010. As like previous case, since how many bits of address your directory is using, since it's using only one digit, I'm going to take the last one digit 0. When I go to this particular 0 entry in your directory, so it is making me to point to bucket A. So bucket here in this particular example, what is the blocking factor we have considered? 4. Means capacity of each bucket can store 4 records. Already 4 records are here. Now this 5th record which I want to insert, it is also generating the same address, and it is telling that you need to insert that record whose key value is 10 into this bucket A. But bucket A is already full. Now what should I do? See here, collision happens. I can't insert into bucket A, there is a collision. Since there is a collision, what should we do? In the earlier slides I told, when the bucket is full, what should we do? We should split that particular bucket. Which bucket I need to split? Bucket A, because bucket A was full, right? I need to split this bucket A into bucket A will be there, plus additional one more bucket. See, that's what I'm trying to do. Split bucket A into A and C. See, this is A will be as it is. Additional bucket, I have bucket, additional bucket is C. Okay, A bucket, because overflow was here, I split the bucket A into A and C. Okay, so what should I do next? See, what should I do next? Double the directory. See, why should I double the size of the directory? Doubling the size, what I have done is just whatever is there in the previous directory, I have copied that as it is. Whatever was there in the previous directory, I have copied as it is. When you have to go for doubling, you can see here the local depth value of your bucket and the global depth value of your directory are same. When local depth and global depth are same, and if one of the record is also pointing to the same bucket, then you need to double the size of the directory like this. Doubling the directory is nothing but whatever was there in the directory, I have copied as it is. No change. Whatever was there earlier, 01 was there, 01 is there. So it was pointing to bucket A. Same thing, now with the first entry is pointing to bucket A. See, no, I have copied as it is. Okay, when you need to double the directory, when the local depth is equal to the global depth, and if some record also basically points to the address of the points to the bucket where already a bucket is full, in such scenario you need to double the size of the directory by copying whatever the contents of the earlier was there. Now I have doubled it. Now what should I do? Add a 1 bit to the left. Add one bit to the left. Now, in the earlier case, I had only 2 buckets. How many bits of addressing was there? Only 1 bit of addressing was there to address 2 buckets. Now, in our example, okay, so how many buckets I have? 3. More than 2 I have. Since I have more than 2 buckets in my example, in order to address these 3 buckets, how many bits, minimum number of bits that are required to address? At least 2 bits. That is 2 power of 2 becomes 4. Means 4 locations I can address. 4 buckets I can address. That's the reason I have added 1 bit to the left. 1 bit to the left I have added. Correct? Now what should I do? Reset the pointers. Okay, so before resetting the pointers, I need to reset the pointers where this particular pointer should point to. So how did you reset the pointers? Basically, you need to distribute the elements. See here, distribute the elements whatever is there in the bucket among A and C. Whatever the elements that are there in the bucket A should be redistributed across bucket A and C. So how do you redistribute? So again, you know that, for example, see here, what is happening? 4 is equal to 100. This was a binary value, the fourth one, because we need to redistribute. And now 12 value you have, this 12, again it is, say for example, same thing. See here, 32 you had, this is the binary value, this is the thing. Now, in this particular case, in this particular example, how many bits of address you need to use in order to distribute the elements? 2 bits. Earlier case, only 1 bit we were using. Now we are supposed to use the 2 bits. Right? Last 2 bits I am supposed to use. So when I use last 2 bits, it points to 0, 0 bucket, 0, 0 only pointing to bucket A. So there is no change. 4, 12, 32, 16 points to bucket A itself. Now our intention was to point 10. What was the last 2? Now I need to take 2 bits. See, that's what the global depth has become 2, and local depth also should become 2 here. Global depth also should become 2. So how many bits of addressing you are using in order to tell this entry belongs to which particular bucket? How many bits of address? 2 bits I'm using now. See, last 2 bits I'm supposed to use. Correct? When I use last bit also, this doesn't change. Which was the one I supposed to insert? 10. Last 2 bits 10. So which bucket it should go? See, 10 is been inserted here. See, we have changed the local depth to 2 for bucket A and C. You can observe what is the local depth of a bucket B. It remains same because only it was using 1 digit. It remains same. Now, so I need to change the global depth. Global depth should be max of your local depth. So I need to make this to change to 2. Global depth also becomes 2. Correct. So now, let me consider similarly, I want to insert 15, 7 and 9 to this particular tree. Okay. So when I insert, see, it becomes like this. How many digits I need to take now? 2 digits, last 2 digits, 1, 1. So I'll go to 1, 1. Pointer is pointing here. Now, again, this bucket B is full. What should I do? Split bucket B into B and D. You need to split, collision happens. Split bucket B into B and D. See here? Bucket B and D. Okay? Bucket B and D. Now reset the pointers. So actually after redistributing the elements present in B, you need to reset the pointers. This I have shown before itself. Right? So redistribute the values. We need to redistribute. Okay? How do you redistribute? For example, you know that for 1, what is the last 2 digits? For 5, what's the last 2 binary digits? 21 last 2 digits. 13 doesn't change here. It remains the same. Which was the element I was supposed to insert? 15. 15 last 2 digits is 1, 1. So it goes into this particular bucket where the global depth basically becomes what? Local depth becomes 2. Here also I need to change my local depth to 2. This I was supposed to change. Correct? See here? 2 it has become. Okay. Now how many? Why? Because how many digits I made you use here in order to show like which bucket an entry should belong to tell that which bucket an entry should belong to. 2 bits I made use. That's the reason the local depth has become 2. Okay. See here, h of 7. Last 2 bits is 1, 1. I'll go to 1, 1. Since it is free, I'm going to insert that value there. Okay. Similarly, 19. See, h of 19 is equal to binary equivalent last 2 digit. If I extract, it tells that 1, 1 bucket. So there is a space in bucket D. So 19 goes and sits into bucket D. Clear? Clear for all of you till here? Now, for example, say, I want to insert 20. Say I want to insert 20. This was our tree. This was our tree till now. After insertion of all the elements, this is the status of a tree what we have. We have 4 buckets. Okay, global depth is 2 and local depth is also 2. And in few buckets are already filled and few buckets still they are empty. Okay, wherein I can insert the elements. Correct? So now, what do I do? Again, find the binary equivalent of this. 20 will be given as an input to your hashing function. Correct? 20 will be given as an input to your hashing function. So it basically returns the same value 20. This is the binary representation of that. So now how many digits I need to extract? 2 digits. Okay, 2 digits if I have extract. So where should I go? Basically, I should go to the appropriate, say for example, this particular entry in your directory. So where it is taking me? It is taking me to bucket A. If you can see bucket A, already bucket A is full. Why? Capacity of a bucket is, we have taken size of the capacity or size of the bucket or capacity of each bucket is, they can store 4 records, wherein the blocking factor of a bucket is 4. So 20 is also pointing me to the same bucket A, which is already full. Yes or no? It's already full. So basically it's a collision. Whenever a collision is happening, basically I need to check, I need to basically increase this particular or split this particular bucket A. Okay, so before I split this particular bucket A, I need to check if the local depth of the bucket, if it is equal to global depth, and it is causing me an overflow in this particular bucket. Since global depth and local depth are both are same and it is leading me to a collision, what we are supposed to do is, okay, as I told you that I'm supposed to split this particular bucket. A, which bucket? Because overflow is caused in this particular bucket, I've split this particular A into A and this additional bucket E. Yes. Now, what should I do? What should I do? Reset the global depth. Why? Because here I'm going to use 3 bits. I'm going to use 3 bits here. Till now I have only 2 bits. With the 2 bits, global depth was equal to the local depth, and since there was an overflow here, so what should I do? Double the size of a directory. How do I double the size of the directory? Whatever is there here, whatever is there, the directory here, same thing I'm going to copy. This is how I'm going to double the directory, and the pointers is also pointing to the same buckets as like what your earlier thing is pointing to. Okay, so after doubling the size of the directory, what should I do? Add 1 bit to the left of this particular directory, because now I'm supposed to use 3-bit address. With 2-bit address, local depth was equal to global depth, and since it was causing an overflow in the bucket A, I have said I have basically split the bucket A into bucket A and E. In order to address 5 buckets, 2 bits of address is not sufficient. Yes or no? To address 5 buckets, 2 bits of address is not sufficient. With 2 bits of address, I can basically address only 4 buckets max. Since the number of buckets has become 5, now I need to use 3 bits of address. Yes, in order to go for 3 bits of address, I need to basically double the size of the directory, and I need to add, okay, 1 bit towards the left. See, 1 bit towards the left I've added. And I need to redistribute whatever the key values was there in your bucket A. I need to redistribute those particular records among bucket A and bucket E. So after redistribution, this is what I got. Now we need to take only for bucket A and bucket E, we are using 3 bits. Because this was a bucket which made us overflow. This bucket we have split. Because of this addition of bucket E only, we have doubled the size of the directory. Since we have doubled the size of the directory, we need to redistribute the elements present in bucket A among bucket A and E. That's the reason now we are going to use 3 bits of address. So for 32, if you consider 32, so binary equivalent of 32 I should take, last 3 bits of the binary value I should take. Now I need to decide whether that goes into bucket A or bucket, say for example, E. So now, after redistributing the elements, original elements present in bucket A among A and E, this is the scenario what you can observe. Okay, now what should I do? I need to reset the pointers. I need to basically reset the pointers. Where exactly? Say earlier, since after doubling the directory, we have copied whatever is there as it is. We have added 1 bit towards the left. After redistributing, we need to reset the pointers. We need to reset the pointers and distribute the contents. Correct? So this is how basically your extendable hashing works. Okay, hope so you have understood how extendable hashing works, how the global depth and local depth, when it gets changed, when should you go for doubling the directory, all those particular stuff. So after understanding this is the overall summary points basically we need to understand. In the example, last example, for whenever we were inserting a record whose key value was 20, okay, so the last 2 bit 00 tells us that the record belongs to bucket A, yes or no, or A2, but not which one, yes or no. So what did we do? We have used the last 3 bits, okay, in order to tell which bucket that particular record whose key value was 20 should go for, right? So local depth of the bucket. So now you should be in a position to understand what exactly a local depth of the bucket. So local depth of the bucket is nothing but number of bits used to determine if an entry belongs to this bucket. So whenever I want to insert, whenever I want to distribute the elements, whenever I want to distribute the records among the buckets, you need to tell that how many bits of address I need to use in order to tell that that particular entry should go into which bucket, right? So those number of bits, the number of bits you're going to use to determine which an entry should belongs to which bucket is nothing but local depth. Similarly, what is your global depth? Global depth is nothing but a maximum number of bits that is needed to tell that which bucket an entry belongs to. Okay, so that's a basic definition we have understood. Now, when does bucket split causes directory doubling? So that also we have seen when the local depth value and the global depth value both are equal. And if you try to perform the insert operation, if the insert operation causes the local depth local depth to become more than the global depth, if the insertion causes the local depth to become more than the global depth, then in that scenario we need to double the size of the directory. Correct? After doubling the size of the directory, we need to redistribute the elements present in the original bucket across the original bucket and the splitted bucket by using the appropriate number of bits, that is nothing but your local depth. So after distributing the elements, you need to reset the pointers to point to the appropriate buckets. Correct? So that's what basically we have seen. Use the least significant bits, enable efficient doubling via copying the directory as it is. Okay, that steps basically whatever the steps we have followed. Right? So comments on your extendable hashing. If a directory fits in the memory, see, we have two things here. One is nothing but your directory. Second one is nothing but your buckets. Okay, so basically suppose if the directory, whatever you're creating, if a directory exactly, if it can fit inside your main memory, whenever you're performing the various file operations, if your directory exactly fits in the primary memory, then whenever you're performing equality search, what is equality search? For example, I want to check if a person with so and so name is part of your file. Or if I want to check if a person so and so with the age is part of this particular file. Yes or no? So if you want to check a particular student with so and so USN is part of the file. Such type of searches are nothing but called as an equality search. Okay, I want to check, they'll give me the student name. They'll ask me to check whether that particular student is a student with a particular name is part of the file. So such searches are nothing but called as a equality search. Okay, so whenever you want to perform the equality search, and if your directory is, if you're able to fit your directory inside your say primary memory, then you can perform such type of equality search in exactly one disk access. You can have an one disk access to your hard disk, and you can tell that yes, whether a part of a student with so and so USN number is part or not. Suppose say if you as we have seen in the example, the size of the directory also goes on doubling. Correct? Size of the directory goes on doubling. Suppose if the directory size is such a way that where you cannot fit exactly into the primary memory, then at least you need two disk access to tell that or to perform the equality search. Okay, so that is the thing. Why? Because directory size will be going on, size of that will be increasing. You will not be able to accommodate that particular directory exactly in the primary memory. In such case, okay, so basically you'll be having more number of entries. Since more number of entries will lead to more than one disk access to tell that if a particular student with USN is present or not is. Correct? So now another scenarios. Okay, insertion we have seen. When insertion may lead to the doubling the directory size, splitting the bucket. Now the another scenario what we need to say, if I go on deleting the entries from the file, if I remove the data entries from the file. So in this particular case, what happens, the buckets may become empty. When the buckets becomes empty, again similar to your B tree and B plus tree, we need to see that if the neighboring sibling buckets are having the entries less than the minimum what they're supposed to have. If it is having like that, then what we can do is we can merge those particular buckets, and if possible, we can try to reduce the size of the directory. Okay, so that's what basically you can do. That is how basically you can make an addition and deletion based upon the number of entries what the user is going to make. Okay, hope so you have understood. Okay, till here clear. So we'll stop here and we'll continue.